Hi everyone, so my name is Byrne, and thank you very much for this opportunity to share our study into spatial cross-validation during the generation of a new indoor radon risk map for Ireland. So just quickly an outline of what we covered today. So we'll look at the background on radon and why it's important to map, and a bit more on the background to this test study specifically and the work it builds upon. And then we'll run through the approach taken and into the outputs. So firstly, what's radon? So it's a radioactive gas that's colorless and odorless, and it's formed in the ground by the radioactive decay of uranium that's present in all rocks and soils. So why do we need a map? Radon can cause lung cancer if the concentrations are high enough. So the EPA Radon Risk Map is a guide to householders and employers as to whether high levels of indoor radon are likely to be found in their building. So the national reference level here is 200 becquerels per meter cubed for homes and schools. And the radon risk map shows the likelihood of those reference levels being exceeded. So why do we need a new map if we already have one? So our current map was devised in 2002, and it looks like this. And it's at a scale of 10 kilometer grid squares, which is quite coarse for a country the size of Ireland, really. And we've seen instances of high levels of localized variation that aren't reflected in the current map. So we wanted a higher spatial resolution for our indoor radon risk map. So to that end, we have some background on previous work that was done. So this test study follows on specifically from a research project carried out in 2018 by the Geological Survey of Ireland and Trinity College Dublin. So if we consider that radon occurs in bedrock, this research from TCD and GSI applied a logistic regression model to predict the likelihood of radon levels above the national reference level. And he used 4 geogenic factors as explanatory variables and the indoor radon measurement points as the dependent variable. So those geogenic factors are taking into account the bedrock, the quaternary geology, the aquifer type, and the subsoil permeability. So we can see the output from that study is the predicted probability map on the right. So it's a clear improvement for spatial resolution compared to our current 10 kilometer grid squares. But before adopting this revised map as the EPA radon risk map, a full assessment of the methodologies and the data was carried out. So this presentation covers specifically the introduction of standard and spatial cross-validation and the assessment of other modeling options. So if we look at the aims of this study, the overarching aim is to ensure the most defensible radon risk map is adopted. And my background is in spatial analysis and spatial data science. So I'm not a radon expert, but the GSI and TCD people who were involved in this previous study are. So their continued collaboration right through this test study was key to achieving the aim of the most defensible radon risk map being adopted. So aside from that, we wanted to have predictive performance metrics for the model so that we could compare it to any future methods that may be proposed in time. And we also wanted to assess the sensitivity of different modeling options or different modeling routines to spatial cross-validation. So if we hop into the approach taken, I guess at the outset, spatial cross-validation is a pretty processing intensive routines to implement. So we tested modeling routines first using standard cross-validation and then selected the top performers for spatial cross-validation only. So if we look through at our data considerations, obviously all of our input data is spatial. So that was key to this. But our dependent variables, so those indoor radon measurements that we have had about 32,000 almost points of those, but only 12% of them were in the positive class. So only 12% were over that reference level. And that's what we're trying to predict. And then our geogenic characteristics are provided by those 4 categorical fields for bedrock, quaternary bedrock, permeability, and aquifer type. So Our imbalanced target influenced quite a few things for a lot of our decisions in the processing. So our metric selection, our model parameters, and ultimately the introduction of sampling strategies as well. So if we continue on into the model selection and standard cross-validation section of things, then on our metrics point of view, we looked at a lot of different options, but ultimately settled on the precision recall area under the curve, as it focuses on the minority class, so it tended to be a little more sensitive in this instance, and we often see it being used in imbalanced modeling problems. So this is the metric that you'll see throughout the results for the rest of the presentation. And we also implemented an evaluation framework for all modeling routines that were implemented so that everything was assessed in exactly the same way. So on the models that we implemented, then obviously we stuck with our logistic regression, as this is our baseline that we wanted to compare all other options to. And we introduced further 4 classifiers for decision tree, random forest, bagging, and boosting. And each of these models then were tuned using our metrics and run through our evaluation framework. So a subset then were used, and sampling strategies were applied to try to alleviate the impact of that imbalanced data. So your sampling strategies, or undersampling strategies, I should say, try to reduce the number of samples in the majority class, so those samples that are of low radon readings, and our oversampling try to generate new samples in the minority class. So many of these techniques that we've looked at, so there's 9 here in total, 6 undersampling and 3 oversampling techniques. So many of these will allow you to decide what the distribution you want to sample towards. So where possible, we sample towards a 50-50, a 70-30, and an 80-20 sample distribution. So to get to our results then this is just from standard cross-validation. So we're trying to hone down the number of models we have that we then bring through to spatial cross-validation. So these are a comparison of the precision recall area under the curve results from the final cross-validation. And at this point, this is a subset of the highest performing ones. So at this point, we've actually evaluated more than 70 different modeling routines. And this graph just shows the highest performing ones without any sampling, those with undersampling, and those with oversampling. So ultimately, we selected logistic regression as our baseline. Our boosting model was actually the highest performing without any sampling. Our bagging with edited nearest neighbor undersampling was our highest performing overall. And then finally, our random forest with random oversampling at 50-50 was our highest oversampling option. So these 4 were then brought through for spatial cross-validation processing then. So on spatial cross-validation, the method we used here was, so actually if we look first at standard cross-validation, essentially considers all the data in the table and then splits it into test data and training data, but does this split randomly, and this is done intentionally to minimize the chance of any dependence between test and training data. But as we all know, spatial data is slightly different. So in doing that random split and not taking the spatial location of the points into consideration, we may actually introduce unintentional bias, as they may be close to each other. So with spatial cross-validation, instead, we consider the data where it is located spatially and randomly select the test points and then create a buffer around that, each of those test points, and any point that's within that buffer cannot participate in the training data set for that run. So in this instance, we implemented that stepwise from 0 to 10 kilometers and 1 kilometer steps. And at each one, we performed 5-fold cross-validation and calculated the averaged precision recall area under the curve for each one. So in doing that, it allows us to track the model performance as the test and training data become increasingly further apart. And this method is built on an adaptation of another published paper from one of the Finnish universities. So if we look at the results, we have in this graph, we have the dead zone radius. This distance is progressing along the x-axis, and then the PR score is on the y-axis. So we have a steady decline, I guess, from as the distance on the as the dead zone radius increases, we can see that steady decline for most models. It's worth noting that after 10 kilometers, we've essentially buffered out the entire Ireland. So no, we couldn't proceed beyond a dead zone radius bigger than 10 kilometers. And we also see that models that need both classes to operate had no high radon measurements in the training data by 6 kilometers and 8 kilometers. So you see that with the bagging model, and the logistic regression kind of runs out at 6 and 8 kilometers respectively. We also see this unusual spike in performance for random forest and XGBoost after about 5 kilometers. And that looks exciting at first, but in fact, when we looked at the training data sets that were being used at that point, the models essentially had insufficient data to be able to operate properly. So they had both the training data sets were both too small and too imbalanced at that point. So if we do remove those kind of erroneous elements and summarize the outputs, it starts to look like this. So this is showing the average PRAUC results from spatial cross-validation for each of the models. And the marker sizes show the percentage difference between the spatial cross-validation and its standard cross-validation equivalent. So at the outset, it looks like bagging with edited nearest neighbors was the highest performing model, and logistic regression was the lowest. But we note the y-axis does not have a very big range, so there actually isn't much of a functional difference in performance really through any of the models in many respects. The other thing to consider as well, or the other thing that we felt was important to consider, was that the outputs of your bagging model are prediction, or well, they're rankings as opposed to probabilities. So in order to use these, we need to further calibrate and therefore define the breakpoints to use in the output mapping. So considering the small difference in the performance metrics between logistic regression and bagging, we ultimately made the programmatic decision that the logistic regression model was the most appropriate thing to proceed with. So that's how we came to this final slide. So this is just showing the progression of the various maps. So the current map on the left-hand side, our 10-kilometer grid. The one in the middle then is the output from the TCD and GSI research. And our final one here is again logistic regression, same as the TCD and GSI research. But you'll see that there is a slightly different distribution. So that's partly due to an updated version of the model itself, as it's been tuned using cross-validation. But the main difference that you're seeing in the distribution of the different levels of probability is as much due to an update of the actual geological data sets that were being used to produce the map. And also in the preceding years, since 2017, we've had more indoor radon measurements taken as well. So this final map is using all available new data. So up to about 40,000 indoor radon measurement points are being used at this point to train the model. And this is our final output. So this new map is due to be published early next year. So that's all from me. So thanks very much for listening, and take any questions if we have any.
Thank you for your presentation today. Anything environmental, as mentioned on our panel, is a topic that our registrants overwhelmingly wanted to hear about. So really appreciate your time today.
Excellent. Hope everyone enjoyed it.
So a couple of follow-on questions for you. In your analysis, did you consider model averaging or making an ensemble model of the best performing models?
Yeah, I guess we did. But ultimately decided not to, for a couple of reasons, really. I guess we'd still be met with that, the, the, the need to calibrate the outputs of that again, similar to we did for to what we saw in the presentation there. And the other side of it as well is, I guess, I mean, there's always something else you want to try, and at some point you kind of need to stop. And I mean, in this case, we'd reached an output that we were satisfied was reasonably defensible. So yeah, we kind of stopped at that point. But there's also quite a lot of other research projects ongoing into this area as well. So using entirely different techniques. So it's not like it's not the end of the road for indoor radon mapping, I guess.
Absolutely. We have a question from Alejandro in the chat. Which are the locations most exposed to high radon exposure? It looks like he had a correction in there. He meant population. So maybe which are the populations most exposed to high radon exposure?
At the risk of sounding like a smart answer, it depends on where you are. I mean, it's yeah. I mean, it there's a couple of things that depends on, or well, that depends on. So I mean, you've all of the explanatory factors that we used in the generation of the map, like they were chosen because different bedrocks will yield more or less radon, I guess. And then, I mean, if radon surfaces to an open field, it dissipates and it's not harmless, or it's not harmful. The problem arises then when it comes into a building and it can actually build up. And whether or not it builds up in a building depends on the building and how the people using that building, or whether how they're actually doing that, like, you know, whether or not it's well ventilated. Things as simple as whether or not somebody tends to often have a window open, not because of radon, just because they like to have the window open. You know, there's simple things like that. Like, so it's this map and this indoor radon risk map is only that. It's only going to say where there's a higher probability of high indoor radon. It doesn't necessarily mean that if you're in a high radon area, therefore your building will have high radon levels. Similarly, if you're not in a high radon area, that doesn't mean that you don't have high radon either. Like, the only way to actually know whether or not a building has high radon levels is to test the building, like, which isn't a testing isn't an expensive or an invasive process. It's really quite easy, and always the guidance from the EPA here in Ireland is just test your building, regardless of what the map actually says. It's a guide, that's all.
Absolutely. We have a follow-on question. You mentioned some of the variables that can impact the exposure, and Freddie asks, which are the variables that best explain the final radon exposure?
Yeah, I mean, it largely comes down to bedrocks, like, so, or well, the geology underlying. So the four that were used in this study was your bedrock, your quaternary geology, the soil permeability, which is kind of more trying to gauge how much can actually raise the surface, or where that may happen, and the aquifer. And, like, it really is a combination of all of them. I'm not trying to give a smart answer, but yeah, it's the combination of all of them, and that was the whole point, I guess, of this analysis, was when you look at each of those none of them individually, but all of them put together. Yeah, where do you get the highest levels then, or the probability of the highest levels?
Absolutely. Appreciate your candid answers on these. I know we're a little bit over time, so I have one final question for you. How easy is it to rerun the model, and are there any plans to update the map regularly as new data becomes available?
Yeah, it's an interesting one because I mean technically it's quite easy to rerun the model. So everything, this whole process from the data preparation start of it right through to the final map output is all pretty much entirely automated. So if there is an update to any of the input data sets, technically it's quite easy to generate a new map, but there's a lot of implications to generating that new map then afterwards. Like, so I mean it feeds into our building regulations, and you've so just things, there's a lot of stakeholder engagement that needs to happen then as well, and a lot of awareness campaigns and a lot of communications stuff. um, so yeah, there's a lot of implications for a lot of stakeholders if you update the map. So yeah, so I mean I guess yeah, it technically it's a straightforward process, but yeah, in reality, all of those other peripheral activities that have to happen, or that's a bigger deal.
Fair enough. It's less straightforward than we might think, it sounds like.
Yeah, as is often the case, the technical end is quite straightforward, but it's all of the rest of it.
Absolutely. Thank you again, Claire. We might have some extra questions in the Q&A if you